What's going on, everyone? In today's video, we're going to go ahead and look at direct variation and go over very quickly how and why they are different and how they can be used to really simply model real world problems. Let's go ahead and dive right in. Okay, so this might be particular to certain textbooks, but the symbol for variation is often denoted as this guy right here. Okay, and what it basically just means is that you're taking k, which is just some constant, and then you're multiplying it by something that happens to follow. In this case, in our power functions unit, we can write something like this, where y is going to vary directly with x to the power of n. And all this means that there's going to be some constant k that is going to be multiplied to our power function x to the power of n. And the reason why it's direct variation is that because as this side gets greater and greater, y is also going to get greater and greater. They are directly, they vary directly. As one goes up, the other one goes up as well. And then on the opposite side, now for inverse variation, we have 1 over to the x to the power of n, which basically means that k is going to be this numerator here over x to the power of n. What this means is that now these two variables are related inversely, meaning that as one goes up, the other goes down, and if the other one goes up, the other one goes down. They're not directly proportional, they are inversely proportional, they're inversely related. So what does that actually look like in a problem? Let's take a look. So now let's say that the distance, which is, let's say, d meters, that a rock falls, is going to vary directly with the square of the time taken t seconds. So now, we know that it's going to vary directly, so we're going to have something that kind of looks like k x to the power of n that we just covered. Now, if the rock falls 6 meters in 2 seconds, let's write an equation for d in terms of t. So what we know to start with is that the distance is going to vary directly with the square of time. So it's going to vary directly with the square of time. That's how I'm going to make it look like the example above. So the distance is going to vary directly with the square of time, which means that I can also say that there's going to be some constant out here that we're going to multiply t by in order to maintain this relationship. So the rock is going to fall 6 meters in 2 seconds. Let's write an equation of d in terms of t. What that means is, what is the value of k here? Because remember, k is a constant. So my d, my distance falling, is 6. I don't know what k is. T is going to be my time in seconds. That's 2. So 6 would be equal to 4k. K would be equal to 3 over 2. I now have my constant value. So what that means is that distance is going to be 3 over 2 times the square of time. I now have a directly... I now have an equation that represents how distance and time vary directly with my constant 3 over 2 using this power function. Now we can actually use this to figure out some information about the problem. So let's say that we don't know how much distance the rock has fallen. We want to figure out what's happened after 5 seconds. Well, I now have a power equation that makes this quite easy. I know that d is equal to 3 over 2 times t squared. And again, just like our last few problems, I now have an input and I want to solve for the output. So I want to know what distance is. I don't know what that is, but I know that 5 seconds is going to be there. So if you go ahead and you put this into your calculator, what you're going to find is that d is equal to 37.5 meters. That is how far the rock has fallen after 5 seconds. Kind of like a very basic gravity problem that you see in physics. So that's how we can use direct variation in order to figure out an equation that can give us an output for a given input. Okay, I hope that helped you see how we can use direct variation in order to set up a problem that we can get information out of. And in our next video, we'll go ahead and take a look at how we can use that for the inverse relationship. See you all in the next video.